Okay, so I'm hoping that seeing that expression for arc length up there is a good place for you to be with number 4.
I was running with it.
Hey, Meg, pause for just a second. So,
I'm out.
hey, guys. For number 4 here, hopefully we would recognize we're doing the integral from t equals 0 to t equals 1. And then it's the square root. It's that distance formula concept. Inside there would be dx dt squared. So that would be 2t quantity squared plus dy dt quantity squared. So that would be 12t squared. And since you don't even have to evaluate this, frozen. Since you don't even have to evaluate that as far as getting to a finished product, that would be it. You've written an expression involving an integral for the arc length of that particular curve, and so you're done. Are you guys okay with the idea that arc length is the same thing as total distance that a particle would travel?
Yes.
And so when we get into vectors after Thanksgiving, we'll spend a couple days on vectors. You're going to feel like a lot of this was the same. You're going to say, whoa, so the total distance traveled for two-dimensional vectors is the same as arc length in parametric? Yes, it's exactly the same. So hopefully we'll be able to make some good connections there when we get to vectors. Yes, ma'am?
So why, when it's like a normal function, not a parametric?
Like y in terms of x?
Yeah.
Mm-hmm.
Is it 1 plus?
Were you here yesterday?
I don't remember. I know you talked about it.
Yeah, I'll tell you what. I'll just
watch
use.
the video again.
No. Like I just made a brief connection yesterday. I'll just use a board here, and I'll kind of show you how they both develop. I'll show you how they both develop. Yeah, for sure. Okay. So beyond that, are you guys okay with number 4?
Mm-hmm.
Okay. So then the other one we didn't do before was number 6. So if you would flip over to that one and see if you can do that one. And Meg, I'll show you. So what we did, I'll kind of give you the back end of both of these proofs.
Okay.
So with regular, right, where y is a function of x, we eventually, like we had like the limit with the sigma, with all this junk, and eventually we're like, hey, you know what, it's actually integral from a to b of square root dx squared plus dy squared.
But then dx squared would just be 1.
Say again?
Dx squared would just be 1.
Nope. So what we did is we recognized, like, this could be in terms of x or y, really. And we said, okay, if this is going to be in terms of x, which typically, if we're dealing with y in terms of x, will be a function of x. And so usually x will be our variable of choice.
Right.
So we said, hey, A is in terms of x, B is maybe in terms of x, something like that. So then we need the differential to be a dx. And so what we did is we factored. And what we did is we factored out of each term. And maybe I'll tell you what, I'll do the order a little bit different. I'm going to factor something out of both of those terms. Nick, if you could maybe slide your slide a little bit. What I'm going to do is I'm going to factor a dx squared out of both of those terms.
Okay.
So if I factor a dx squared out of this, that's where this becomes 1, right? Plus, if I factor a dx squared out of this, there isn't a dx squared in there. And so I just got to remember factoring out is really dividing out.
Okay.
So this would be dy squared over dx squared, which is really dy dx quantity squared.
That makes a lot more sense.
So with parametric, we've got to recognize that your independent variable is always going to be a t. So instead of and then let me finish this real quick. So then this is where you get 1 plus this, like we just said. And then the square root of dx squared is just dx.
Yeah.
So then we end up with like so. So then with parametric, when we set this up as integral from a to b of the same thing, basically just the distance formula, and we say, all right, well, we need a differential to go with our integral here. Then we look back over here and we say, well, gosh, these are parametric, and so this is actually in terms of t. Like this is from t equals a to t equals b. So I need a differential over here that matches that,
So,
and neither one of these are that. So what I need to do is instead of factoring out a dx squared out of both, I need to factor a dt squared out of both.
okay.
So this is where I'd get this, and I'm factoring out a dt squared. It'll eventually come out as just a dt.
Yeah.
But then I just got to remember that factoring out is really dividing out. So dx divided by dt, well, that would just be dx squared over dt squared. You can see that first part taking shape, and then same thing here, dy squared over dt squared. And then you could, similarly square root this little differential, get the dt out, kind of like we did over there with the dx. And that's why this doesn't end up being a 1,
Okay.
because you're not dividing it by itself.
Okay.
Yeah,
Thank you.
you bet. Wouldn't our candidates for a highest point be like maybe a horizontal tangent line?
Yeah.
Could be a lowest point, could be a highest point, but that's at least what we'd investigate, plus endpoints as well. So what I'm going to do here is find dy dt. Dy dt is equal to -2. I don't know if did you have negative on that, Sam? I can't remember. -2 sine of 2t? Yeah, sine of 2t. Okay. And I want to set that equal to 0. And so then I get to this sine of 2t equals 0. I do the inverse sine of both sides. For what angle is sine 0? So that'd be something like 0, pi, 2 pi, 3 pi, ... right? Got to go around the circle as many times as we need to get all the possible angles here. So let's see here. If I then solve, I would get t equals 0, which is not in my domain, so that's out. Pi over 2, that's barely in my domain, isn't it? It's barely, so that's in. Pi, that's in my domain. And then 3 pi over 2, that's slightly out, isn't it? That's just like a little bit bigger than 4.5. Okay, so I stop there, I get rid of this, I get rid of that. Those are my two places where dy dt is 0. We always want to check to see what dx dt is doing. It might give us a hint about what the graph might look like. We want to see if dx dt is also 0 at either one of those. So dx dt would be 2 cosine of t. Okay, so then, 2 cosine of pi over 2 is 0. So that tells me that right here, I don't know, can you tell me what that means? What don't we have? No, nothing about vertical. Either one, let's be honest. Not asymptote, though, tangent line. So I don't have a vertical, I don't have a horizontal tangent line.
Those are the words that I want.
Something weird is going on. It could be a sharp point, it could be nothing. We just can say for sure that it's not a horizontal tangent line, it's not a vertical tangent line. Okay? But we can still consider that as a candidate because it could be a sharp point. But if it came down to a list of, hey, what are the horizontal tangent lines? Pi over 2 wouldn't be it. Right? That could be a sharp point. It could be a point of where the graph just doesn't exist, or it could be nothing. It could be all kinds of stuff.
So why doesn't 0 work?
Because it's outside the domain. 1.5 to 4.5. Otherwise, it would work. Otherwise, it would work just fine.
So you evaluate for the domain after you solve for t completely?
Say it one more time.
You evaluate if it's inside the domain and not after you solve for t completely?
Yeah, you really can't do that until after you've got the t all the way by itself. Yeah, because when you have 2t equals, still have to divide by 2. It's not that hard to tell, but
Yeah.
I usually wait until after.
Okay.
Yeah. Okay, so then I'm going to plug my t in. I'm going to plug my t in for the input of x or for the input of y. Which one would make more sense here? Y. WHY.
Right.
No, I'm asking you, why would we...
Because we're looking for the highest point.
Highest. What would plugging into x tell us?
Left or right?
Most right or most left? That's right. Okay, so then I'll just say this is y equals cosine of t right here. I've got my endpoints, which are 1.5 and 4.5. I've got my one strange input that, you know, nothing might be even going on there. I don't even know. And then if, oh, it is cosine 2t. Thank you. So I just need to plug these in, use the calculator at least on the endpoints. So cosine of 3, that's got to be close to -1, doesn't it? It's like negative 0.9 something or other. What is that? Negative
0.990.
990. You plug in pi over 2, actually get -1. Plug in pi, we get 0. Or 1, I mean, yeah, because we're talking about cosine, not sine. And then cosine of 9, I don't even know. What is that?
It's about -0.911.
911?
Yeah.
Okay. So then all we have to do now is look at those outputs and ask ourselves which one's highest, right? Because we're looking for the highest point. So we'd say the highest point, and this is where, kind of like yesterday, I pointed out that we could make a real mistake here and say the highest point is pi comma 1, right? That's not really the highest point. Pi is the time when we hit the highest point, and 1 is the y coordinate. But if I'm looking for a point, I need the x and the y, right? So instead of pi comma 1, I could say that I know that it's something comma 1, but how would I find the x that would go with that?
Put t of pi to the x, 2 sine of 2.
That's right. So sine of pi is 0, and 2 times 0 is 0. So it looks like 0, 1 is our high point on our graph. And we're done. So just be careful, like when it uses the word point, know that we're talking about like an x comma y coordinate on a graph. Sometimes it'll say find the time when it's at its highest or whatever, and then you just list out t equals pi for that. All right. That's it. That's practice. I'll be here to help if you need any help or questions or conversations about any of those things. Let me know. But you have your homework 2. Gets into all the calculus of this. So I'll be around. Santi.
For homework 1,
Uh-huh.
really less, probably like the
Just
sine,
solving.
cosine
Yep,
one.
I was about to
Can I leave